times you'll be given data sets or data tables like this and be asked to determine the rate constant or the rate expression. So first off, determining the rate expression is where you have to start. You have to come up with what the formula is. So again, the rate expression for this would be the rate equals the rate constant times the concentration of A raised to some power times the concentration of B raised to some power. So we're not done. We need to determine what the rate, what order the rate is with regards to A, and what order the rate is with regards to B. So there are two ways you can do this. The first way is to do what's called some table logic, just do some deductive reasoning, and the other is to do it mathematically. Personally, I'm a fan of the table logic because it works a lot quicker, a lot faster. So we have to figure out what order of reaction is for each reactant. Let's look at A first. So if I was doing an experiment, the best way to figure out what order a reaction is, if I was doing an experiment, the best way to determine the variables in the experiment is to determine where something stayed constant. So I'm going to look at what effect changing the concentration of A had on the rate. I'm going to want to keep the concentration of B constant. So I'm going to look for where the concentration of A changed, but the concentration of B did not. So concentration of A changed in 1, 2, and 3 was the same in 1, 4, and 5. But in 1, 2, and 3, the concentration of B stayed the same. So let's do one that's easy to look at. Let's compare trials 1 and 3, because that's easy to see. We have a concentration of 0.5, we have a concentration of 1. So if we doubled the concentration of A and we kept B constant, what effect did that have on the rate, the initial rate? Well, the initial rate stayed the same. So between from trials 1 to 3, we can say that by looking at trials 1 and 3, where the concentration of A doubles, the rate stayed the same. Therefore, the rate with respects to A must be first order. So we already have our first one right there. Let's go ahead and plug that into our rate expression. Now we're going to do the same thing with B. We're going to look for a trial in which B increased by a measurable amount and A stayed the same. So if I look at trials, let's clear some of this first so we can look at it clearly. Let's see, if I look at trials 1 and 4, the concentration of B doubled very clearly. The concentration of A stayed the same. What happened to the rate? Well, the rate doubled as well. So we would say it the same way we did before. Looking at trials 1 and 4, where the concentration of B doubles, the rate, therefore, with regards to B is first order. I've got to clear this up. Sorry, the rate for A, since it stayed the same, the rate with regards to A would be 0 order. So again, looking at trials 1 and 3, where concentration of A doubled, and therefore it's the rate, but the rate stayed the same. The rate with regards to A is 0 order. Looking at trials 1 and 4, where the concentration of B doubled, the rate also doubled, therefore the rate with regards to B is first order. So our rate, our reaction rate expression would be the rate equals the constant times the concentration of A to the 0, which we can just cross out and put 1 there, or just get rid of altogether, times the concentration of B to the first. So that's using the basic table logic. We could then plug in, what we're going to do later, we will plug in values and solve for K, because that would usually be the next step in a problem. I'm going to show you the mathematical way of doing this as well. In Also, if you look at this, the overall reaction rate or the overall reaction rate order for this problem would be first order because 0 plus 1 is 1. You can also find these values mathematically, which takes a bit longer, but it always works. And it just uses some ugly algebra. To find the value for m or n, or the value for these question marks up here, I'll change them back to question marks. You're simply going to write the rate expression for two separate trials, and then solve for what m or n would have to equal. Now, you'd be really smart if you picked any lines of data. I mean, you can pick any lines of data, but you'd be really smart if you selected trials where one reactant concentration is held constant so that it cancels out of this overall expression, since you don't know what m or n equals. So if we were going to solve for m, first off, I'm going to pick trials. Let's just pull one and 4. So 0.5 and 0.5 and m cancel each other out, and 0.5, actually these 10 to the negative 2's also cancel each other out, so we have half equals 1 half. So in this case, the k's also cancel each other out, so we have 1 half equals 1 half to the n. So in the case of b, n must be 1. And you can do the same for finding m. Again, I prefer the table logic because it's much quicker, and on a multiple choice question, time's of the essence. But regardless of how you would have done the problem, you would have come up with the rate equals the constant times the concentration of B to the first. We can plug values, any values from any of the trials, not any values, you can plug values from any one of the trials into this equation to solve for K. So let's plug in from trial 2. So 0.5 times 10 to the negative 2 equals some value times 0.2 to the first. Divide by 0.2 on both sides. You find that K equals 0.025. But now you have to determine whether the units. Alright, to determine the units, this is the hardest part, you have to simply do, the units are whatever per the time, and then the molarity is whatever the reaction order is. Sorry, the dog's interrupted me. So again, the units are, not again, but the units are per the time unit. So in this case, it's going to be per hour, and then it's molarity to the 1 minus whatever the reaction order is. So overall, this is a reaction order of 1, so this would be per hour molarity to the 1 minus 1 is 0, so molarity to the 0, so we can outright ignore it. So this would be 0.025 per hour. And I put the molarity there to see that it's 1 minus 1 would be 0. So this was, again, the reaction order is 1. When we subtract 1, we end up with 0, so we can ignore that.